All right. So from the beginning of this unit, I've kind of said that, regression is something best done on a calculator, on a computer, what have you. So what I'm going to do today, or what we're going to do today, is look at what a regression actually looks like when you run it on the computer. So what this sheet has is it has a bunch of different statistical packages, Minitab, JMP, Excel, that can do regression. And they all output the results in slightly different fashions. So I wanted to kind of show you these so that you would understand how to read a computer output of a regression. All right, and then in another video, I'm going to show you how to actually do one on the computer. But this right now is just so that you understand how to read one of these, because again, this is generally how you're going to do regression if you're doing it, outside of a school setting. You won't be doing it on your calculator. You'll be doing it using some sort of statistical package. All right, so let's take a look at this first one here. So the coefficients are what we're generally going to use for our equations. So right here in this Minitab output, the coefficients are going to be what you use as the equation. Now, different programs will label these differently, but in this case, the constant is referring to your y-intercept, and body weight for this case would be your x value. All right, so if we were to write out the actual equation, this would be y hat equals 16.265 plus 0.09080x. All right, that's how we can pull the equation from this computer output. All right, the standard error of the coefficients, we don't need to worry about right now. T-stat, p-value, again, will become relevant later in the course. These terms will mean something to you, a t-value and a p-stat. A t-value, a t-stat and a p-value. But for right now, you don't need to worry about what's happening there. All right. This S right here that you're seeing, this is our standard deviation of the residuals. All right. So when you're running it on a computer program, it's going to get you that value automatically. You don't have to go through all the steps that we have to go through to get it on a graphing calculator. Because again, a graphing calculator is not really meant for statistics. So when you actually run it on a computer program, it's going to have all of that for you. All right. Then there's R squared and R squared adjusted. All right. R squared adjusted is when you're using or when you're performing multi-variable regression, where you have lots of x's. So this is the one that we're going to use, right? This is the one that we want to use because we're only doing one variable regression. And again, this is the percent of variation in the data explained by our regression. And as I said last time, you can almost kind of think of this as like the grade for your model. So it's how well your model is doing at explaining the ups and the downs. How well does this variable explain whatever you're trying to predict? All right. So again, that's how you would read that first output. All right. Now the second one, you're going to see a lot of the same things, and you can actually match them up by looking at the values, but it is presented in a different way. All right. They both have the t values. They both have p values, but they're labeled different. All right. They both have the standard error, but they're labeled different. All right. What they called the coefficients, this one's calling the estimate. All right. Same values, just different labels. So you just want to make sure that you don't get, tripped up just because the different outputs are labeling things in different ways. I mean, this one's much more explicit, where it says intercept, so it should be pretty obvious that that one is your y-int. And again, this would be your x value here. All right, this one tells you the number of observations. It tells you the mean response, all right, which the other one didn't. But then what it calls the root mean square error is what we've been calling standard deviation of residuals. All right, they mean the same thing. It's just different names for the same concept. So again, on a quiz or a test, you don't know which one I'm going to be giving you. So you have to be able to look at any one of these and say, oh, okay, root mean square error. I know that's actually standard deviation of residuals. R squared versus R squared adjusted. I know that the R squared is the one that I want to use. All right. So again, it's important that you're able to kind of look at these and say, all right, this is the one that I want versus not the one that I want, and so on and so forth. Now, notice that neither of these give us the correlation. So if I wanted to know the correlation, I could take my R squared value and take the square root. So for both of these, if I wanted to know the correlation, I could take my R squared value, which is 0.631536, and take the square root of that. All right. So 0.631536, I would get 0.7947 will go. All right. And then the sign is the same as the slope. Because remember, correlations can be from -1 to +1, whereas the R squared value is always going to be positive. So when we take the square root, we have to consider, is it positive or negative? And basically you can look to the slope. If the slope is positive, the value is going to be positive, or the correlation is going to be positive. If the slope is negative, the correlation is going to be negative. Right? So again, just kind of being able to read one of these, being able to find different values from this. Now here we have Excel. All right, so let's take a look at the Excel output, because this is the one that you're going to probably be using the most. All right, so again, there's a little more going on here, but most of it we can ignore for sort of our purposes right now. All right. We don't really need to worry about this whole ANOVA section. I mean, is that stuff important? Sure, but it's not anything that we need to worry about right now. So you can kind of just ignore that part. Again, here is what we're using for our equation. All right, so this is where our equation is coming from. Again, you're seeing t-stats, you're seeing p-values. This is what's called a confidence interval. You don't have to worry about any of this right now. For what we're doing, you just need to be able to get the equation, which again, there's our y-intercept, there's our x value. So this is that same BAC equation that we were dealing with before. So we're looking at y hat equals -0.015 plus, we'll say, 0.019x. All right, but recognizing that these are the numbers we need to write our equation. Again, standard error right here. If you remember from the notes last time, this was the standard deviation of our residuals, 0.02. That's what we calculated last class. So they're calling it standard error, but again, this is our standard deviation of the residuals. So kind of annoying because we're seeing 3 different outputs and all 3 of them label it differently: standard error, root mean square error, just S, but in all cases, it's the same value. And no matter which output I give you, you should be able to identify the standard deviation of the residuals. Again, R squared is the one we want to be using right here, not R squared adjusted. So this is our R squared value. And then for our two variable situations here, this value is our correlation. But again, you have to look to the slope to make sure that you're getting the right sign on your correlation. So here our slope is positive, so our correlation is also going to be positive. Okay. All right. So again, just making sure that you know how to read these outputs and get the information that's encoded in them. So let's just practice this a little bit. So here's a Minitab output. It says, what is the regression equation? So from this, what's the regression equation? And there's two ways you can write it. You can either write it as y hat equals, again, the constant would be our y-intercept, so 18773.3 minus 86.18x. Or the more useful way to write it is to put it in context. So this is using mileage to predict the price of a Honda. So write it like this: predicted price equals 18773.3 minus 86.18 times miles. All right, and then that makes your equation a little more readable so that people kind of understand what it's saying. All right, what is the standard deviation of the residuals? All right, that would be right here. All right, so 971.647. And then it says how much of the variation in the data is explained by the model. All right, you have to recognize that this sentence is referring to the R squared value, which for this problem, it gives it to us as 76.4%, or you can just write it as 0.764. Now, just to illustrate the point here of correlation, if you wanted to know the correlation for this one, it would be negative and then the square root of 0.764. And the reason it would be negative is because the slope is negative. So the slope is going to tell you the sign on your correlation. And then it's just the square root of 0.764, which for our case is like negative 0.874. So you can't just take the square root. You have to pay attention to the slope to get your sign. All right. And then again, this is just another one down here. So it says age of first word used to predict Gessel scores, which is like a reading measurement. So again, just recognizing that your regression equation is coming from these estimates here. So y hat equals 109.87384 minus 1.126989. And again, you could times x. You could put in the actual words here. So this would be age. This would be predicted score. And then that just puts the equation into context. All right. Standard deviation of the residuals we have to recognize is root mean square error. So that's our 11.02291. And how much of the variation in the data is explained by the model? Again, that's our R squared value, which in this one is just labeled up here at the top. So you don't want to be using adjusted. Adjusted is for multivariable, and we're not doing multivariable. So 0.409971. And again, this question doesn't ask for it, but if you wanted the correlation, again, because the slope is negative here, it would have to be the negative of the square root of 0.409971, which, if we do that quick, what's it work out to be? Negative square root 0.409971 works out to be like negative 0.6403. Okay, so again, information that you can pull from these outputs. Again, I will put up another video that shows you how to actually do one of these on the computer, but this is sort of the outputs. These are the types of outputs you'll see, and you just want to make sure that you're able to interpret these and figure out what's going on. All right. Last little thing that we're going to do here is a final sort of summary of the regression unit. All right, so there's not really anything left. We've covered everything that we're going to cover in this unit, and this is just kind of a final summary of kind of what we've been doing here. So the first point says the distinction between explanatory and response variables is important for least squares regression. This is not the case for correlation. All right. And again, this goes back to the formulas, and this is why we learn the formulas. All right. The formula for slope is R times SY over SX. Division is not commutative. So if we flip the order, it matters. Correlation is the sum of all the zx times zy's divided by n minus 1 is based in multiplication. All right, flipping the order here doesn't matter. Flipping order doesn't matter because it's multiplication. Flipping here does matter. Flipping order doesn't matter. All right, flipping order does matter. All right, so kind of keeping that in mind. Correlation and least squares regressions are only useful to describe linear relationships. It's not enough just to look at your R and R squared. A lot of times people want to do that. Like, oh, I've got a good R, I've got a good R squared, I'm all set. You have to plot your data in residuals. All right. These values only have meaning when the data is linear. So you can calculate them no matter what, but they only have significance. They only mean something when the data is linear. So it's not enough just to look at these values and say, oh, we're good to go. You have to look at the scatter plots. You have to look at the residual plots to make sure that you're dealing with linear data. So when you're looking at a scatter plot, you're hoping that your points kind of follow a straight line and there's no obvious curves. All right, so you're looking for a linear form. When you're looking at the residual plot, you're hoping for no pattern whatsoever. All right, so you're hoping for no pattern. So there's a difference there. With the scatter plot, you're hoping to see a pattern in your points, and they should have a linear form. With the residuals, you're looking for no pattern. All right. Next thing, association does not imply causation. So we've got all these regression models. They give us predictions, but just because two variables are correlated does not mean that they cause one another. All right. We don't have evidence that our X is causing Y to change. We're just saying that they're associated. There could always be a lurking variable that is driving the association. All right, the example I gave in class was with COVID and eating at restaurants. And they said there was a high correlation between eating at a restaurant and eventually catching COVID. That does not mean that eating at restaurants causes you to catch COVID. It might be that people that eat at restaurants take other risks, and it's those other risks that are causing them to catch COVID. So again, correlation does not equal causation. A high R squared or R doesn't mean one thing causes the other. All right, so don't fall into that trap of being like, oh, this totally explains why this is happening because there's a high correlation. It might just be that they're related. All right, so be careful with those. Correlation and least squares regressions are not resistant. All right. So one unusual point can have a major impact on the value of R and therefore the regression equation. Because remember, the regression equation uses R. The slope is R times SY over SX. So if one unusual point can have a large impact on R, which we saw with our correlation values, it can also impact the regression. So here we have a scatter plot. All right, this is the line that came from it. And we could argue that there are two sort of outliers. Child 18 is way out here on the X. Child 19 is way up here on the Y. Both of those could be considered outliers. All right. What this graph down here is showing you is it's showing you how just removing one point can drastically change the equations and the values. So this is when all 19 children were involved. This is without child 19, so this one right here. And this is without child 18, so this one over here. And it's just showing you can see a pretty wide swing in the correlations, negative 0.64, negative 0.76, negative 0.33. And the equations themselves change quite a bit too with the slopes and everything else. You know, we go from a slope of a maximum slope of 1.19 down to a minimum slope of 0.779 just by removing like one point here or there. So again, outliers have a major impact on correlation and by extension, a major impact on the regression equations. Now again, this right here is our R value. You can also see that it's going to have a major impact in our R squared value because those two things are directly related. So if we do 0.64 squared, our R squared for this one would be 0.41. If we do 0.76 squared, our R squared for this one is going to be 0.58. And if we do R squared for this one, it's going to be 0.11. So again, everything's sort of connected here. So those one outliers can have a major impact on all of the things that we're calculating. And by extension, your equations, your correlations, your R squareds, all of that stuff can be drastically impacted by an outlier. And then this down here just says outliers can be considered influential if removing the point would markedly change the results of the regression, right, which is what we're seeing here. And points that are outliers in the x direction of the scatter plot tend to be more influential for the least squares regression lines. So this is that thing that we were saying before, that points at the edge, or we'll say edges, because it could be either edges of the distribution, have more impact than ones in the middle. And points in the middle. All right, that's basically what this last one is saying, which we've seen time and time again with our correlation stuff. And again, correlation is directly tied to regression, so it's all connected. All right, so again, this is just kind of some summary stuff here to kind of wrap up the unit and kind of give you some big thoughts to think about as we move on to our next topic. All right, so there is still going to be another video that shows you how to actually do the regressions on the computer, but that's it for this one. So as always, reach out if you have any questions. Bye.